Good day everybody, and welcome to the second CPD webinar in our series covering the topics of how to model existing drainage systems and flood mapping with XP Swim. My name is Peter Coombs, and today's webinar is focused on how to model a river or creek or wadi, including a range of typical structures such as culverts and bridge crossings. We will show how to investigate the impact of a new drainage system that will outfall into the river. We will also illustrate the consequences of poor maintenance. This is on critical structures such as culverts. And I'm pleased to introduce you to two of my colleagues who will be actively participating in the webinar with me today. First of all, Samer Mohandes. Samer has recently finished his Master's in Civil Engineering at the University of Greenwich after he did his undergraduate degree in Syria and then worked in Cairo as a construction site supervisor. Following on from Samer, Ludmila Fadeva. Ludmila is a drainage engineer with 8 years of both design and modelling experience in the UK as well as overseas. And when I say overseas, I specifically mean the Middle East. Now, due to the numbers attending the webinar today, we've had to mute everybody, but do feel free to send us any questions in the GoToMeeting message box that you'll see on your screen when you first logged into the webinar. We will either answer them live during the event or we'll provide a full written explanation that we'll share with everybody afterwards. And at the end of the webinar, we will be uploading this particular webinar as a video onto the website. We'll issue a frequently asked question sheet covering the questions that we've received, and we'll be sending out a short survey monkey to enable you to feedback, request a CPD certificate, and any other topics that you feel that you'd like us to cover over the subsequent series. So here's the agenda for today's webinar. We've designed it to last for about 30-40 minutes, and that includes an opportunity for you to ask questions, so maximum of 1 hour during the lunchtime, if you're in the UK, for example. And what we're going to do is run through sequentially, handing over to Samer, who will then hand over to Ludmila, and then pass back to me live with the software. Now, during the seminar, what we'll do is not only share best working practice, but also emphasize the quality and the speed at which we can model and, very importantly, extract this information to provide those results in a format that the approving authorities require. If you're listening in from the UK, we have specific requirements for the EA over here, and I'll show you how you can extract that information to update their particular surface water flood maps. Samer is going to start by modelling a river and then setting up the pre-development condition, so the natural catchment condition for this particular area. And then after that, Samer is going to set up a second scenario, and that is to model the post-development condition. Now, after the post-development condition has been set, Samer will hand over to Ludmila, and Ludmila can then focus on the critical structures and show how to assess the impact of poor maintenance on those structures, poor maintenance that can lead to sedimentation and blockages in culverts, in bridge areas, etc., etc. Following that, I will share the range of outputs available to satisfy the needs of those municipalities, the public themselves who need to be educated and informed, and those approving authorities such as the Environment Agency. So without further ado, it's now my pleasure to hand you over to Samer Mohandes, and Samer is going to cover modelling a river and how to generate a flow in a watercourse.
Thank you, Peter. Hello everyone and welcome again. As Peter mentioned earlier, we will cover 1D, 2D integrated river modeling. So first of all, I will explain what is 1D modeling and what are the elements for 1D models. 1D hydraulic models use cross-section to represent the channel, bridges, and pipes. These cross-sections will be joined to form the rivers, pipe networks, and flood plains. They are normally or essentially link node-based models. In 1D models, we will use continuity and momentum equations to determine velocity, discharge, and flow area in the links. The vertical and lateral flow characteristics are not considered in 1D models. In 1D models, we will be dealing with nodes, links, and when I say links, they could be pipes or river links, catchments and catchment connections, as well as cross-sections and water level lines. 1D models are very easy to troubleshoot. They need less time, less data, and less hardware equipment, as well as there is plenty of literature available for 1D modeling. However, 1D models cannot model the shallow overland flows correctly, as the flow pattern is essentially 2D. 1D models tend to overestimate the water depth and velocity due to 1D assumption. The storage effect is taken into consideration in 1D models only in nodes and not in channels, and that is not accurate and doesn't reflect the physical reality. In 1D models, you need to predict the flow direction before 1D modeling when you don't need to predict it in 2D modeling. In 2D models, we will be dealing with grid extents, active and inactive areas, 1D and 2D interfaces and connections, hidden flow boundaries, flow constrictions, and rainfall grids. XT-Swim will link 1D and 2D models together through water levels and flow calculated by XT-Swim. The integrated 1D 2D models means that we will have 1D network and 2D grid system coupled and simulated simultaneously. The advantages of this approach are that we're going to get realistic and more accurate results. We will have simultaneous integration between 1D and 2D, and we will need less engineering judgment. With this approach, 1D 2D integrated models, we can model the flood flow routes, simulate the storage effect in the channels, which will reflect the physical reality, simulate bridges and many other hydraulic structures, create flood inundation maps, as well as we will see in the next webinar. So now we will model the river as 1D, and then we will link it to 2D and see the difference between 1D models and 1D 2D integrated models. So first of all, we will generate our river cross sections from the digital terrain data. This is a very easy and preferable way in case we have accurate topography data for the river beach, as normally the data which is generated from the LiDAR is not accurate enough when it comes to the river. So I will show you how we can get our cross sections from the digital terrain data. We are going to right click on the river link and click on Define Cross-Section Layout. So here, all we have to do is to draw one line where we would like our cross-section to be, and then we will have our cross-section ready. We can right-click again and click on Edit Data, and from here we can tell XT-Swim where we would like our left bank and right bank to be. And remember, you can always override or modify the river's cross-section in case we don't have accurate data. We can also import our cross-sections from HICRAS, as Lumina will show you later. After we simulated our river, something to notice that our river is considered now as a dry river or as a wadi, as there is no inflow data into the river. The inflow into the river could be generated either from inserting hydrograph at the upstream end of the river or at any node. So what we can do, we can double click on the node and go to User Inflow and insert the hydrograph data, which will be time flow series. Or we can connect our existing drainage network and make it discharge into the river, so we will have flow from the 1D network, and that's for the post-development. We can have inflow into the river from the storm water which is running off due to rainfall on a grid, and that's when we connect 1D to 2D to have 1D 2D integrated models. Now I will hand you over to Ludmila. Ludmila will show you how to model a culvert, blockage, and a bridge. Over to you, Ludmila.
Thank you, Summer. Now I'm going to show you how to model a blocked culvert. We do have two scenarios, pre and post development. I will leave the culvert as free-flowing in pre-development and make it blocked in post-development scenario. If I zoom into my culvert location, double click on a culvert link, click on conduit factors, we can see a tables here. In here we can see different parameters to change. For example, sediment depth, inlet type, energy loss coefficients, and many others. By modifying sediment depth, we can represent conduit blockage. So this parameter is directly representing the conduit blockage. I'm going to leave it as 0 in pre-development scenario, and I'm going to have a value in post-development scenario. So in post-development scenario, the value is going to be 1.5 meter of sediment. It means that my conduit is blocked by 1.5 meter. Now I'm going to check how the blockage affects grade line in dynamic section. I will select the river from beginning to the end. I will go to pre-development scenario and press and click on dynamic long section. I can see that in pre-development my conduit is not blocked and the hydraulic grade line is somewhere 2/3 of a conduit height. If I do change the scenario to post-development and go to long section again, we can see that the black color is representing the blockage, 1.5 meter of blockage, and my pink hydraulic grade line now is much higher than the actual conduit depth. So the effect can be seen straight away. Next structure I would like to cover is a bridge. First of all, I will zoom into the bridge location. I will double click on the bridge link, and firstly we would need to enter such data as high chord elevation, low chord elevation, skew angle, wear coefficient. The next step would be to identify our hydraulic opening. So I will click edit, and this is the location where we can identify our hydraulic opening for the bridge. So you can see that my opening is identified. The bridge can be different types. We can have a simple pier bridge. It can be 1 pier, 2 piers, 7 piers, as many as you like. Or we can have a bridge which could be a different shaped bridge, for instance, covered bridge, or a bridge with a bypass, or an arc bridge. So if I want to show a bypass in any bridge, I would just select a second opening as a culvert circular and show it as a bypass here. I can have invert elevation, length, diameter. As well, my bridge can be few sections of rectangular conduits. Then I can have as many openings as I like, all being rectangular conduits. I can have the height and the width, as well as the length and munnings. And for instance, I can have 5 openings like this. Or I can have a user-defined section, which can be any shape or type you like. When I'm using conduits, I can as well use conduit factors. So this is the same table as with culverts, where we can specify the sediment depth. So for instance, if we do have a bridge which would consist of 5 openings of rectangular culverts, we could block maybe 2 of them or 3 of them and keep another 2 free-flowing. So then we can represent the bridge blockage. In our today's case, we are not going to complicate the modeling process. We will just keep a 2-pier simple bridge. But one thing to notice, that in XP Swim you do not need to specify each section of a pier bridge. As you know, our hydraulic section is now divided into 3 separate sections, but we do not need to identify each section separately. We just say that this is our bridge, these are our piers located at X coordinate with such and such and exit and entry losses with such and such munnings, and the program will model the whole section together. Finally, I would like to demonstrate you how to get some numbers out. For instance, I'm interested in river water levels pre and post development. And I'm interested in freeboard values in pre and post development. I'm very much keen to know what is happening in node number 60. So I'm going to select node number 60, go to pre-development, and click on XP table. What I can see, node number 60 is highlighted in yellow. It is because it's selected. So if you select a couple of nodes, 3, 4, or 5, all the nodes or links you selected would be highlighted in yellow. So it's very easy to find them in the table. Maximum water elevation I'm interested in is 41.152. And my freeboard value at the moment is 1.4 meter. As well, you can notice that I have few nodes which are with 0 values. This is my future drainage network, which will be with values in post-development condition. But because it is switched off in pre-development, all this has 0 value. So it is not counted, there is no flow coming in. So this is purely the river and the inflow hydrograph which some are identified in the beginning. So now, if I'm going to switch to post-development condition and go to tables again, we can still see that our node number 60 is highlighted in yellow, and now our maximum water elevation is 41.659, and my freeboard value has reduced to 0.890, which is about half a meter more water or less freeboard than to pre-development condition. By using the tables, we can define any parameter we like in a tabular way. We can manually select which column will be first, second, or third. We can have as many columns as we like. We can export them to Excel, and we can do some mathematical comparisons within the tables. Similarly, when we do go to long section, and we check in here, all what we have specified in table to be shown is shown in the long section as well. So sometimes you don't need to go to table to actually see the result. You can read it from the long section. As Summer mentioned, I'm going to show you how to import HECRAS model, because we did have many questions coming out of our first webinar, how actually to do it. So I do have a separate model here, for which I do have a generated HECRAS model. So what I'm going to do, I will click File, I will click Import Export Data, I will click Import HECRAS Data. I do need to select a HECRAS model, so I do select G01 file, which was designed and developed within HECRAS software. I click Open, and I do have two options. To import all network, it means it will import all the hydraulic structures, or import cross-sections only. So sometimes we don't want the structures, we want the sections only. Say if we are doing a new design and we want to change the structures. But in my case, I'm going to import all network. So I will just press OK, and here it is. I do have the river imported. So now just let's check. I know in here that there is a bridge. As you can see from Google Earth picture, there is a bridge. And a bridge has been imported. And if we double click, this is the bridge. We do have all the data which was specified in HECRAS. And we do have the hydraulic opening, and we do have the piers which were specified in HECRAS model. Imported into XP Swim. And if we just click on a simple river link, we can see that the link has a shape, and if we go edit, we can see that it was imported and left and right overbank as specified as per HECRAS model. So this is a straightforward and very easy way to import your ready models which were generated in HECRAS. Now I'm going to close the HECRAS model and hand you over to Peter, and Peter will tell you how to describe the results of our modeling.
Thank you, Sama. Thank you, Ludmila. So what I'd like to do now is use the models that Sama and Ludmila have created, and then share the all-important outputs. In fact, what I'll do, let me just have a quick look at the slide presentation because there are some specific ones that I want to focus on. Knowing the audience that we have here today, a lot of people have asked us about extraction of these particular results for submissions that potentially go into updating surface water flood maps. Now, this is a key requirement, and this document came out that I'm showing on the screen here in May of last year, May 2013. And apologies, don't worry about looking at all the detail in the spreadsheet. I think you're going to be bamboozled by the columns and the rows and the size of them. But basically, what I want to do is cover items such as the model domain outputs, the depth of the water, the flood water, the velocity, hazard rating, and also the flow directions. And if you just look on the right-hand side, you can notice that there are some preferred file types that the Environment Agency would prefer for your models to export out as. And what I'm going to do is show you how to export those results in accordance with those particular file formats. Now, if you're not in England, then that's not a problem, because if you'd like to let us know the formats that you are interested in, we can also maybe show you how to do that in future webinars. So I look forward to those questions. This particular document, if you don't already have it, is really useful, and you can read up on those depth, velocity, hazard requirements, as well as the direction of flow, and it's really clearly stated in a range of sections there, and a particularly good read. So what I'll do, I'll go back to the software and let me show you how to extract this information, and I'm going to initially start off by looking at the left-hand side of the screen. We can see that there's a reporting section. So by clicking on reporting, there are a range of things that I can share with you, and I'm going to look at, first of all, the 1D, but then focus a little bit in more detail on the 2D and show you how to extract those particular data sets. So looking at the 1D on the left-hand side, I'm going to click on 1D flood maps, and towards the bottom of the screen, there's an option to be able to put on the minimum or the maximum flood depths as a visual created in the 1D model. And the legend on the right-hand side has been color-coded. So we can see for this post-development situation, looking at the top here, there's a post-development, and bear in mind you can always flip between the pre and the post-development scenarios. We can see that we've got something like a ½ meter of water. The lighter blue and the green is getting up towards 1 meter depth of water. So this is showing you the maximum depth that's in the channel and actually coming out of the channel in certain areas. But as Samra mentioned earlier on, this is identifying flooding at nodes, where you have these virtual basins. It doesn't give you the true representation and that dynamic flow over the surface, and maybe we have properties affected or farmland or whatever that we need to look at. We can see more information with the 1D, and I'll share another couple of views with you actually, because there is a dynamic plan view. And this is now the plan of the section, and looking at the top of the screen, I could either show the flow or the velocity. So I can look at both, and I can run the analysis of this in kind of real time, and you'll now see flows in the links and flows through the nodes, and these are shown in the legend on the right-hand side. So if we had red flow in the links, this is telling me that we would be up at something like 28 cubic meters per second. And if we had red nodes, they would be flooding. I can do the same thing for the velocity, and then just run the animation for you. So minute by minute, we can see, here we are, it's just going to run. I can pause this, so when you get to an interesting point. So for example, here, I'm looking at the orange in the links. So this is now telling me that my velocity is running at something like 2.4 meters per second within the channel. I can see that we have some flooding at the node. There's a red flooding indicator down towards the downstream end of that water course that Ludmilla shared with you earlier. And notice this kind of white wiggly blue indicator. This is showing you where this is the flood indicator. Okay, so this is telling you this is where the floodings take place. You can see flow coming through the drainage network and feeding into the channels at a variety of nodes. I'll close this view because it's showing you the 1D and concentrating on that, which I'm really interested in. But now, if I close on that, I'll take a look at the long section, the dynamic long section view. So I'm going to click, hold the Shift key down. There we go. That's it. And hold the Shift key down. There we are. And then look at my dynamic long section. Yeah. Okay, so as Ludmilla shared with you earlier on, this is the dynamic long section view. We can switch in between the post-development and the pre-development, or all the various scenarios with the information from those XP tables clearly indicated here. And once more, we can show the animations. Now I know from the document, and here's the flooding indicator further downstream. Now I know from the EA document they're not particularly interested in the animations. The animations are really helpful when we're discussing these flooding issues with the public or within the key stakeholders like lead local flood authorities, the municipalities, environment agency, etc., and those people that are affected. But that's an overview really on what we can extract quite readily and easily in terms of the 1D. Ludmilla has just reminded me that there are a series of graphs that I could also share with you. Thanks, Ludmilla. Now, in terms of the pre- and post-development scenarios, what I can do is graphically compare. This is looking a little bit busy. This is showing you each of the nodes, and it's the water elevations building up during the event. So the event is showing along the x-axis. How the water is shown in either blue or red. The blue being the pre-development and the red being the post-development scenario. Okay, so again, graphically, node by node, where that flooding is indicated, as Simon mentioned, this is how we can extract that information. Okay. So to better visualize where the effects of the flooding would take place, this is where the 1D, 2D interaction really comes into play. And I can see on the reporting to the left-hand side that we can extract a range of information. We can look at maximum water depth. So if I click on that, now you would maybe think if we had flooding out of these nodes at the upstream end of the river, and if we had flooding going across the land, we would see it all. So we could show it all, or we could say, look, I'm not really interested in anything that's, say, shallower than, in this case, 100 millimeters, 10 centimeters. So you could set that to threshold levels, 15 centimeter, or whatever your particular requirements are. So what I'm saying is the water that's shallower than 100 millimeters is not being shown in this maximum water depth slide. Okay. What I can do is look at the animation, and we can run the water depth, okay, which now starts at 0 up to the 4 meters max. So running the animation, I'll just speed this up a little bit. Again, I can pause when I get to an interesting point. Notice towards the upstream end of the river, water level is getting deeper. Okay, we're starting to see flooding coming out of the bank where the blockage is occurring, and then running over the surface of the model. It's running down the digital train model, and it's then re-entering the channel. Okay, so you can see the actual overland flood route kind of minute by minute, or whatever time step you choose to run at. This is now showing you the true overland flow route and the interaction between the 1D in the channel and the 2D across the surface. Now what we can do when we have that kind of information, if I click on the water depth, for example, I can right click. We can reset the properties to change the visual appearance of all of this, as I mentioned, but I can also export the results from here. And I wouldn't expect you to remember the file formats. I'll review this in a second, but notice the output file format options. So we can here extract the information as mapinfo interchange files, Esri grid files, or Esri shape files. And we just hit export. I'm going to just cancel on that. So we have water depths that we're interested in. We can see water elevations. I can focus in on the hazard. So we can look at the maximum hazard scenario. Again, the legend is showing on the left-hand side of the screen here. So this is the velocity times the depth, and we can change the formula if you wish to. You can change some factors within the formula if you have a particular formula that you need to work with and put in some particular parameters. We can edit those. We'll show you that in a later webinar. And we can look at just the hazard rating based on in this particular case, we've set it up to be based on the UK variations. We can also take a look at velocities. Remember that velocity was a key aspect as well. You could set up and look at the maximum velocity. Now this looks quite dense. If I just zoom in here a little bit. So I'm just going to zoom in and take a look at the screen here. Okay, there we are. And notice when I click on the max velocity and zoom in, you have the arrowhead showing you the direction of the flow and also the maximum velocity that's traveled across that particular grid square throughout the duration of this event. So again, really important information, and we can extract all of this in XP tables and analyze to our heart's content. Okay. The other information that I feel is really critically important is when we're planning for flooding events. Now, if I'm working for an environment agency or a local authority, how much time do I have until the velocities reach these peaks? Is the kind of question in my mind. How much time do I have until the water depth reaches its peak? So we have here the two different times, time to peak in terms of velocity, and then I'm going to zoom back out here because this is color coded. The legend automatically shows for me. So you can see that the time for this overland flood routing to peak in terms of its speed is looking at about 2 to maybe 3 hours. It's less than 1 hour within the channel, but 2 to 3 hours across the surface in terms of velocity. I'll take that one off. And let's have a look at the time to peak in terms of the depth of the water. So similar kind of a scenario, but it's indicating how much time the emergency services and the local authorities have to mobilize and help the people that could be potentially affected by this. I'm working with the post-development at all times here because pre-development, this is the original greenfield condition that Ludmila showed you earlier on. Now, the other final points that I'd like to raise is the fact that we can extract all of this information in terms of GIS data by using the tool drop-down menu. So we could just do the right-click on the visuals as we were working through, but then I can also go to the tool drop-down, look at the XP with 2D utility interface, and we've built this into the software such that you can then extract these 2D results into those GIS formats that are listed in the table that I showed for you earlier on. Now for this we would need an input file. We would then set up a 2DM, a .2DM file. This is the 2flow files, by the way. So I just click on the browse to show you, and I'm just going to go to the river model that we were looking at earlier on revision 3. Now this is showing you the file formats, and just remember them. They are .xmdf formats. So we can run a range of scenarios, maybe 30-year, 100-year, 1,000-year, all is required in that table, save them out in these formats. These are file formats that you can then straight submit directly to the EA with them having to do no further work whatsoever other than read them into their models. The .2dm file, if I click on there and go back to our webinar and then revision 3 folder, here we are. So here are the .2dm file formats that we've automatically generated. We then save out as an output file as well and send off to to the EA or the local authorities. Looking at the output properties, there's a format option here, and you can see that you have the three options of ArcGIS shapefile, Esri ASCII grid files, or the map info interchange files. We can also extract those files in terms of the depth of the water, the flow, the velocity, and those actual water levels, the elevations. So all the variety of permutations that are required to update those maps are automatically generated out of here. Now, a really interesting aspect of this and what we've built in here is the grid size. I'm just going to mention the time here. You can change the time incremental, so you can have all of the various runs, etc. But I'm looking at the grid size. We could set up grid cells of 1 meter by 1 meter or 50 meter by 50 meter, whatever, in the original model. But now, extracting, we could say, I want this in a 2 by 2 grid size. This is the grid size that the Environment Agency would like. So it's automatically extracted, and that saves the Environment Agency doing any work whatsoever with that information. So, just in summary, I hope you can see that all of that information in terms of model domain, flow direction, they're all file types that we fully support, and you can extract directly out of the software having run the analysis. In terms of the depth, the velocity, and the hazard, we can actually give you the .2dm file format. We can exchange between the XMDF. Remember the .xmdf file format? We've even got a converter between the .dat and the .xmdf file formats as well, or just save out in one or the other. And I hope that makes for happy consultants, happy local authorities, happy Environment Agency, because there isn't one aspect of that particular table that we cannot now satisfy. We look forward to all of your requests for other formats that you may well want, and I may well regret those words, but I look forward to receiving that information, or we look forward to receiving that information from you. So in conclusion, what we're showing you here now is really the speed at which you can then run these compliant models. And it's the speed of setting up not just the 1D, but integrating that with the 2D and then extracting the results, which for me is what it's all about, because we need to get some positive outcomes. And within the PR14 requirements in the UK through the water industry, it's now not about outputs, it's all about outcomes. And I hope you can see that by working with the technologies that are available nowadays, how quickly and easily you can extract this information and make meaningful decisions and help people that are at risk from flooding events in whatever way they are being affected. I want to just thank both Samar and Ludmila for showing us that really insightful way of setting the models up and doing all the hard work and for providing what I see as a systematic approach to 1D, 2D modeling. And I hope everyone out there can now understand how quickly and easily we can generate river cross-sections directly off the DTM. Now, if that DTM information is based on LiDAR, as Samar mentioned, and you're not too confident about the accuracy of the LiDAR data, then what we can do is import third-party sections such as HECRAS directly to improve the quality of that 1D section. I hope you can see how easy it is to create that integrated model, how quickly we can run the various scenarios, and then also understand the impact of the additional flow coming in from new developments, or maybe the scenarios where you have blocked culverts, or things blocking the bridge crossings over wadis or rivers, etc. And how you can compare those pre and post development scenarios, both graphically as well as in the tabular formats for further analysis, as well as those outputs that are really important to supply to people. The next webinar, by the way, we're planning this for the 15th of October. And I'm just going to check with Ludmilla and with Samba. Were there some questions that you wanted to specifically answer right now?
Yeah, we will answer the questions and send them out after the webinar.
Oh, okay, good. So what was it? We've had a lot of questions here, folks, and what we're going to do, we'll take all of those questions and then we'll produce a frequently asked question fact sheet, and we'll send that out to everybody so that you all have a comprehensive kind of library of information building up through this series of 7 webinars. And as I say, the next one we're planning for the 15th of October. Sadly, I won't be here, but gladly Ludmilla and Summer will be. So they look forward to running that webinar for you. And what that will be covering is what's shown on the screen here now. We're going to look at more detail now in terms of urbanized drainage modeling. So we're going to look at how to model an existing drainage system. So these are typically the pipes, manholes, etc. It could be a range of things that you have in the urban catchment. And look at the catchment areas contributing into each of those nodes and how you can set those up. The key thing from the surface water flood map document is that we need to run a range of scenarios, and those scenarios are based upon the 30, 100 and 1,000 year return periods. So we'll show you how we run those and can compare the various scenarios. And the outcome from that particular event will be inundation maps. And as we go through and get into more detail, I like to focus more on the outcomes of this, so where the inundation has taken place, and then further down the line, we can even predict time scales for evacuation routes. So if the local authorities have particular main roads or routes that they need to keep open, or the emergency services are using them, we can predict and provide you with that information on how much time you have for specific flood routes. So without further ado, I'd just like to thank you all for your active participation and the questions. You're going to keep the guys here busy answering all of those. And please note that if you're interested and you do need to come on some training, we do have 4 days of training that we're running here in Newbury between the 29th of September, so that'll be like a week today. Yeah, it's a week today. And running through until Thursday. So I have to double check, but basically it's a first come, first serve. So if you haven't already booked, I'd suggest you go to the website right now, because we can, if we can't book you on this particular one, we'll let you know when the next service is running, basically. So following the webinar now, I'm going to edit and then upload the video onto the website. The team here, Ludmilla and Summer, will produce a frequently asked fact sheet and send this out to you. We'll send a very brief survey monkey to see what are the topics you'd like us to cover in future webinars, and enable you to request a CPD certificate. So thank you all for attending. Thank you, Summer. Thank you, Ludmilla. Really look forward to keeping in touch and meeting with you online again on the 15th of October. Take care.